All right, so welcome back.
Hey. I don't know. I just felt like saying hi.
So one part of ABET, which is what you all, if you don't know it, UAH is an ABET accredited College of Engineering, which means eventually you can, if you pass the FE, Fundamentals of Engineering exam, you can eventually become a PE, a professional engineer. And that's important because it means that you can actually go work at certain places. Because there's some places like Boeing, I think, unless you are from an ABET accredited university, you can't come work for them as an engineer.
We're going to look at you.
Yeah.
A lot of the job applications say, or job recs say ABET accredited university.
Yeah. So a part of ABET, one thing we have to do is ethics. And so they have decided, the great lords of ABET at UAH, have decided that that should be in the first semester of senior design in both ISE and in MAE.
When we took this, when we were in school, we actually had a class called ethics.
Yep, we did a whole entire class on ethics. So be happy, you don't have to do that much on it.
You studied like Kant and Locke and all that.
Yeah. That dude forgot their names. Socrates.
Socrates,
yeah. And all of them too. But anyway, Plato,
yeah.
Plato, I was going to say Plato. Plato. All that kind of stuff, right? But anyway, so one thing in our senior design class is we have to do an ethics case study, right? So this video is to explain a little bit about it, and then your assignment you'll see at the end is to go download it, you can read some more about it, and then write a 2 to 3 page paper about your assignment in the role of this case, right?
Minimum 2 pages.
Yeah. We don't need, I don't need a paragraph or two like I talked about before in the intro, but I don't need a book either. I need something in between, right?
And it's not like a page and then like a part of the next page.
Yeah.
It's 2 pages.
Yeah, at least 2 pages.
This is not rocket science.
Yeah.
This is counting.
Yeah. So we need to make sure you do that.
Because we have to submit these to the department, and then people from outside the university come and look at these, and they'll be like, "Your ethics stuff is crap," you know? And then then we get docked for it. So this is why your stuff needs to look good.
Right. So the ethics case study that we're going to talk about is the Challenger Space Shuttle Disaster that happened on January 28th, 1986. I remember that very well that day because I was in 5th grade. You were in 5th grade too, right?
Yes.
And I remember being in Gifted, called GATE, Gifted and Talented Enrichment is where I was. And at that point, I didn't care crap about the space program. I was going to be an orthodontist, I think, is what I was going to be. Because I made a lot of money. I remember telling people that. That's what I thought back then.
They still do.
And
it would not have been a bad field.
Yeah. And so they came in and told us that the space shuttle had just blown up. And I was like, whoopee, And they made us write a paper about it. And I thought, I don't care. But then I got really, really, really interested in it. And it turns out I had a big family history in it because that lady right there, Krista McAuliffe, she's the first teacher in space in the space program. And actually my mother, who's a school teacher in North Carolina, she applied and was one of the finalists for North Carolina to be the teacher in space for the space program. But she got pregnant with my sister and so couldn't go forward with it. And so it's kind of crazy, but I didn't realize that until afterwards. So this is actually the crew of STS-51L is officially the name of their mission. And so these are all the people that ended up dying because Challenger blew up on the way up, right? So it's kind of crazy to look at it. Look how grainy. And look, the worm. Now the worm's back. Yep. Isn't that weird? And they actually had the meatball in the worm, which I never realized until now. So, but yeah, all these guys, they're gone, right? And it's been a really long time. It's been
86, yeah.
Wow, it's 34 years. 34 years ago this happened. So this is the Space Shuttle Challenger accident. This is the launch on that wonderful January 28th morning. And 73 seconds later, this is what happened, right? And so this has been a huge, famous story that a lot of people talk about, especially in engineering. The one thing I want you to know about is it just wasn't one thing that happened. It was multiple things that made this occur, right? And that's usually how major engineering problems occur. It's not just some one little thing that happened. It's a whole set of things that have happened over a long time that eventually, finally, the system goes, I'm done, and gets rid of it, and that's what happens. That ends up happening, right? So, a little history. So the Space Shuttle program, right? Because we all, I mean, a lot of us, even and still, probably you guys, not as much, but we definitely do because we grew up with Space Shuttle. That's like the iconic thing for us is this orbiter, you know, this tank and everything flying into orbit. And here at Marshall Space Flight Center, they were in charge of everything except the orbiter, the winged vehicle, right? Everything else was Marshall Space Flight Center's problem. And so they were the ones in charge of it. But the actual beginning of Space Shuttle was actually February 13th of 1969. They created what's called the Space Task Group, right? And the Space Task Group had sat down and thought about, well, how are we going to do post-Apollo, right? Because we hadn't even landed on the moon at that point. But they already realized they needed to figure out what was the next step. And the biggest thing behind that is Apollo was costing a blooming fortune, right? It was $1 billion back then to launch a Saturn V and do all that really cool stuff with it. But we knew we couldn't keep doing that. And there was this thing called Vietnam that was starting to suck up all the money in this country. So the Space Task Group came back and they decided that there were 3 things that we needed. One was a space shuttle, a tug, to get things up into low Earth orbit and back. The second was a space station, right, in low Earth orbit. And then another thing was a Mars vehicle. It was kind of the commonality of all of them. And that's actually what Dr. Von Braun, who was the first director of Marshall Space Flight Center and kind of the god of everything we use right now, that was kind of his plan, is we needed a shuttle, we needed a station, and then we could go to Mars, right? And so he needed the shuttle first. So on January 5th, 1972, President Nixon actually signed the Space Shuttle program. He said, start it, let's figure out what we need to do, right? And so that's what they did. Initial concepts, because the first thing they thought about with the shuttle was that it should be fully reusable, right? So you can see some of the initial concepts. Most of them had a flyback booster and a second booster that would go into orbit, right? And so that was the initial concepts. But they realized more and more, there was a thing called Vietnam, and so it was sucking up the money, and so we couldn't make everything reusable. So we ended up with a partially reusable launch vehicle, right? And so that's what Space Shuttle ended up being. They had decided, who was the administrator then? Was it Webb? One of the administrators went to OMB, the Office of Management and Budget, which is the budget of the federal government, and said, how much money can I have? And they said, you can have $5.5 billion to create the space shuttle. And he went, cool, that's what it'll cost. It ended up costing almost twice as much with what we got. But that's government accounting for you. You know, that's how it works. So the final concept ended up being partially reusable. So that's what we got, right? Was the Space Transportation System is officially what it's called. So the winged thing and where the crew's set up here is called the orbiter, right? And so there's this big, huge cargo bay. It's 60 feet long and 15 feet wide. And so that was the thing to get everything up into orbit. Down here is the Space Shuttle main engines. There's 3 of those on board. They burn liquid oxygen, liquid hydrogen, which is from this big, huge thing called the external tank. It's just a big thermos, is really what it was. The wings actually came from the Air Force. The DoD required that it had a nice cross range to be able to do things, because NASA actually didn't want it to have wings, but they said, sure, we'll give it to you, DoD, because you're actually bigger than we are. So they created this winged vehicle for them, right? So here's the external tank. This is the thing. This thing always came back, right? It was reusable, except for 2 times. Every time it came back. Then there's the external tank. That's the thing that was destroyed every time, right? It re-enters the atmosphere, and we build a brand new one every time in Michoud. At the Michoud Assembly Plant, we call it MAF, outside of New Orleans, Louisiana, is where they were built. That is actually coincidentally where SLS is being built now, because it's a gigantic factory. Mm-hmm. Matt and I actually toured it. We took several senior design students down to tour it. Yeah. And the only way to get across the thing, because it's so big, is you get on a bike. Remember?
They had trucks driving around.
Yeah, too. In it.
Inside the building, yeah.
It's so crazy how big it is. So that's that part. Then the part that we're going to talk about with Challenger more than anything are the 2 big solid rocket boosters, the white things on either side, right? The left one and the right one. These guys were manufactured, right, and built for this thing. They ended up becoming reusable to a point. You get the casing back and you could reuse it partially, but it turns out this actually became very, very expensive. Probably just destroying them every time would have been a lot easier for us. Okay? So all this was a grand compromise, and that's what's going to happen in engineering for you, right? You're going to go into engineering having this pure idea of what it's like, but in the end it's a compromise of a lot of different pieces having to come together, right? And so this is not what any engineer wanted, but this is how the budget went, This is how Congress went. And remember, anything with the federal government has politicians involved, right? Which means you got to keep people very, very happy. And that's a big deal with this thing, right? So the solid rocket boosters, that's the part we're going to focus on. The solid rocket boosters was a compromise of how do you lift this thing off the ground pretty quickly and get it out of most of the atmosphere before it keeps on going into space. So the solid rocket boosters, light at liftoff, they provide most of the thrust. Each of these are 2.2 million pounds of thrust. Think of them as big, huge Roman candles, like you shoot off at the 4th of July. They're just a couple hundred, 150 feet tall. That's really what they are, right? They're made in segments, and the reason why they're made in segments is because they're actually built in Utah, right? So back then, when we did this design in the 70s, they had bids that went out, and the bid that was the lowest, not the best, but the lowest, was by a company called Thiokol, Morton Thiokol Corporation. There used to be Morton Salt. If you've ever looked at salt, you see Morton as the thing. That's their company, right? Because it's salt. It's something you mine. Solid rocket boosters, same deal. You mine the stuff to make it work. So these guys were actually chosen to be from Utah. Well, we launched these things at Cape Canaveral Kennedy Space Center in Florida, right? So the thing is, you chop them up into segments, and you can put them on huge railroad cars, and you can send them across the country. So far, so good. That seemed all to work, right? But the problem is, once you get them there, you've got to stack them, right? And inside here, they are burning aluminum and ammonium perchlorate and HTPB are the three things. They're not even going HTPB. Yeah, they are. A little bit of HTPB, right? And so that's what's inside these things. And so you've got a very, very hot flame. It's several thousand degrees F. So you got to figure out what to do with that. So what you do is you put them together, right? And so you have all these different segments. There's actually 4 segments on a solid rocket booster right now. Eventually SLS is going to have a 5-segment version of a booster, right? And so you can see the different segments here. They have parachutes because they brought them back down, drogue chutes, separation motors, the nozzle, all that kind of stuff. But they joined them together, right? And they're 150 feet long and a little over 12 feet in diameter. So they're pretty big, huge Roman candles. They're the largest solid rocket motors ever made on this planet. And that was another thing that was really interesting because we had what's called the Titan IV launch vehicle that had big solid rocket motors, but these guys are almost twice as big. Then everyone just assumed you could scale up. It wasn't a big deal. That is wrong, right? But these big segments were brought in. There were 4 chunks of them, right? And they were locked together. And it was a tongue and groove kind of thing is how they made it. You can see it right here, the joint, right? So these 2 pieces locked together and made this thing work. And inside here is the propellant where it's lit. And it's, is that the right way? I'm looking at it the right way, I'm going backwards. No, it's the propellant. Okay, yeah. So here's where they are, right? The propellant. And inside here is the lit. And so it's a couple thousand degrees F. And so when they put these things together, what they said was, all right, you bolt them down, you do all this stuff. But because we've had this area that could make this flame go through it, what we'll do is we'll put these O-rings. So we have a primary O-ring and we have a secondary O-ring, right? Just to be on the safe side. We'll put 2 because if that fire got out, it could be a really bad day for us. So when they designed this thing, they decided that was the way to do it. And you'd have this path out, And also what they did is they put putty all along this, because that will become very important, is there's putty that fills in all of this after you do it, right? So that's what they did. Everybody thought this was cool. We could work with it. It went within budget. We could do everything with it, right? So, but there was a history of problems with this thing, right? Very early on, they realized this design and this entire design had some issues with it, right? So in 1977, before we launched, the first space shuttle launched in 1981, right? In 1977, during a hydroburst test, the failure occurred in the joint seals. Both the primary and secondary O-rings leaked, right? So automatically these 2 things, even though they just did a hydroburst, so they put water in it and pressurized it to very high pressure, much like what they would do in a real rocket engine, right? These things were leaking. So they already knew there was an issue, right? These tests indicated some joint openings so that the joints, because remember they're flexing, and so that O-ring, the point was an O-ring they thought when the joint started flexing it would just lock itself down and seal it, If you think about it in plumbing, it's the same thing. When you do an O-ring in there, it's the same kind of idea. but it wasn't working. And so the contrary to the joint designer's expectations. Already in 77 we had a problem, but we had to keep going forward. So everybody went, okay, let's just keep going. We'll figure this out as we go along, right? In 1980, there was the Space Shuttle Verification Certification Propulsion Committee, and it was concerned about leaks in the joints. And so they designated the joint as a criticality 1R redundant hardware failure, right? Which would mean that the total element failure of which would cause loss of life or vehicle. So what they decided was, it was also noted that it was not known if the secondary O-ring would successfully reseal if the primary O-ring should fail. But everyone on the outside world thought, there's two, right? There's one and a backup. So it'll be fine, no big deal, right? So we get to STS-1, Shuttle Columbia lifts off the ground on April 12th, 1981. Everyone's very, very happy. We finally got the thing up there, right? It's finally working. STS-2, right, in 1981. It resulted in blow-by through the putty around the O-ring in the joint. And there was one scorched primary O-ring on one of the solid rocket boosters. So what they ended up looking at, is this putty, and when it gets past the secondary O-ring, even in the primary O-ring, and then the secondary O-ring, it's called blow-by. So the putty actually got pushed all the way through, and that means that the primary O-ring did not seal all the way, and the putty either got caught here or caught here. And so that's called blow-by to them, is what they determined that terminology. And what they noticed was on STS-2, it was happening, the second flight, right? They actually now know, as they projected more and more, if STS-2 would have lasted, if their flight would have lasted, their launch would have lasted a little bit longer with the solid rocket boosters, this thing would have probably failed, and we'd have had a Challenger on STS-2 and not just STS-51L. So that's what's really crazy about that part, right? So that happened. But they kept just creating a committee and saying, well, it did its job, right? Because every time something would happen with the primary, they'd say, the secondary works, we're good, right? And that's what happens in engineering. You become complacent, right? That you go, well, that's what we designed it for, right? So that seems to make sense. That the secondary worked, we're good. Why do we need to worry about it? And that was kind of NASA's whole rule of thumb back then. So in 84, primary O-rings eroded in 3 joints on STS-41B. The erosion on one case-to-case joint of O-ring was basically a lot of the diameter, and so now they were starting to get worried because erosion was becoming a bigger issue. And then in 85, STS-51C experienced the coldest launch to date, which was 51 degrees F. 2 primary O-rings in the case-to-case field joints had erosion, and a primary rings and 2 field and both nozzle joints had soot blow-by. So see, now they're seeing a lot more of it when it's only 53 degrees, right? So that was the biggest issue. So they kept seeing a pattern of stuff, but everybody kind of kept it quiet, right? Except people at Morton Thiokol, the manufacturer of the rocket, the SRB, right? At NASA, everybody's going, it's working, we're good, let's keep going, right? And so that was the primary issue here. So there's mounting pressure on the shuttle, right? We've got all these issues, but there's a lot of pressure on the shuttle to keep it flying. When Congress was told about the space transportation system in the 70s, they said that it will become extremely cheap. That we will fly every week and it will cost no more than $1 million a flight, right? That's what NASA told Congress. That was a big lie. I think the top, even after Challenger, the top flight rate was 9 a year, and they cost more than like $400 million to launch a space shuttle. So it was never going to work, but there was all this pressure, keep flying, keep flying, keep flying, right? Actually, 2 weeks before STS-51L, Columbia had just lifted off the ground. So 2 weeks later, they were flying another one, you know? And it just kept on getting worse and worse and worse. And delays have been recurring. 51L, the 5 in 51L, meant it was supposed to happen in 1985, right? And instead it was in 86 because they kept having issues after issue after issue. You know, something was breaking, something's wrong, this is wrong, this is wrong, right? And the problem was you had this person called the teacher in space, right? Crystal McAuliffe was supposed to go up there, and her job was to say, okay, space flight's very routine, it's no big deal, it's not going to be a problem, right? And so that was the problem, is NASA had all these competing factors going on them, right? Mm-hmm. Also what happened in 1986, because this was January 1986, there's always this thing called the State of the Union that happens. And so there was pressure from inside the White House to make this flight happen, because what they wanted to do was have President Ronald Reagan actually talk to Krista McAuliffe in space during the State of the Union. Because then it would look so cool, we look how powerful our nation is. Because back then, I know all of you were not even thought of back then in 1986, but our big, huge threat was Russia, right? The USSR. And so we wanted to show that we were the technologically powerful nation on Earth. And what better way to do it than to show a teacher, a common person, not an astronaut, not a PhD and all this stuff. I think she's a history teacher, if I remember correctly, Krista was. She was in space, doing cool experiments in space, talking to the President of the United States. That would look so awesome, So there was all this pressure on NASA to make this flight happen. Coincidentally, they tried on January 27th and they didn't get it off the ground because there was a problem with the hatch. They couldn't get it sealed properly. So they tried again on January 28th, right? So all this leads up, because see, that's my point to you guys, is in engineering, it's not just one thing. It's everything coming together that's going to make this thing happen, If one of these pieces wouldn't have been there, we don't know. It might have still happened, but maybe not, And so all that's the big deal behind this. So, the night before the launch, January 27th, a big thing happens that was unbelievable to everybody that was involved. The night before, so the day of the launch, January 28th, down at Kennedy Space Center, which is a tropical paradise normally, right now it's hot as can be down there, but back then in January, it was a really freakish cold front that came through and made it the coldest it would ever be. They had predicted at launch it would be about 25 to 30 degrees F, which was unbelievably outside the bounds, right? The lowest had ever been 53. So they called a big meeting. Morton Thiokol did with NASA to say, hang on, let's talk about this for a minute, right? Because they always do. The night before they have to do launch commit criteria and all this stuff anyway. So they asked for a meeting. So Morton Thiokol engineers, I always say his name wrong, but Roger, I call him Bourgeois, I don't know how you say it really. And Arnie Thompson at Utah were concerned about the damage sustained on the O-rings of STS-51C, which had been the previous cold launch temperature at that point in time, and about the predicted cold temperatures for Challenger's launch the next day. Right? So Thiokol asked for a teleconference with NASA later that evening on January 27th to discuss the issue of O-ring sealing and cold temperatures. The teleconference started at 8:45 Eastern, right, in the evening, and connected with Marshall Space Flight Center here in Huntsville, and Florida with KSC, right, and with Morton Thiokol in Utah. That's kind of the three big things. Morton Thiokol manager Alan McDonald. Alan McDonald was also in Florida for the launch. And there were actually back then, which is, they don't even know what that means, a view graph was sent so they could do it. Yeah, it's a PowerPoint chart, but back then we didn't have PowerPoint, so they actually had to fax them to Alabama, from Utah to Alabama and Florida. I thought that was cool as well to put that in there. So what Thiokol ended up recommending, because they didn't have any other data to work with, was you didn't launch unless the air temperature was at least 53 degrees F, right? And that was the previous temperature for 51C when they saw some problems, but at least it didn't fail all the way, right? Since they didn't want to exceed all that stuff. But the predicted launch temperature was 28 or 29 degrees F, right? And so that's when the Marshall Solid Rocket Motor project manager actually said, my God, Thiokol, when do you want me to launch? Next April, right? Because he knew there was going to be a very cold season in Florida, and so there was no way he could keep up this launch rate. He's supposed to go every 2 weeks back then. They already had another shuttle on the pad. That's how unbelievably fast they were going to launch. And that started scaring Morton Thiokol, because they were actually up for contract rebid, right? So you've got the program manager of the thing telling you, what? You mean your system doesn't work when I need it to? Right? So that made everybody at Thiokol start to freak out, right? And so when challenged, Thiokol engineers admitted they lacked statistical analysis to show the correlation, right? They didn't have anything. They didn't, because the shuttle spec said 40 degrees to 90 degrees is when you can launch, right? So this 29 degrees, though, was still going to be outside the bound, but that wasn't 53 degrees, which is what their system had to do. So all this stuff was pushing down on Thiokol about, really? Are you sure you got to do that, right? So then Marshall asked Thiokol, because they kept talking back and forth, for a go, no-go recommendation, right? Thiokol initially said, no, we do not recommend you launch. They kept the 53-degree F thing, right? So at this point, after more than an hour on the telecon, a Thiokol vice president, so the big thing you need to know about Al McDonald was the vice president of engineering. There was also another vice president of business of Thiokol that was on the telecon, right? And so at that point, that VP in Utah took them offline for 30 minutes, right, to discuss the no launch recommendation, because they realized this was kind of putting the contract on the line for them. So what should they do? Should they listen to the engineers, or do they got to think, weigh the options of what to do? So the Thiokol engineers repeated their warning not to launch in cold. And what happened is the Thiokol business VP actually told the Thiokol vice president for engineering, take off your engineering hat and put on your management hat, right? That is the famous quote of all of this, right? Stop thinking just like an engineer and think about it as a businessman. What's going to happen to us if we go through with this, right? Because one thing will happen. NASA, of all things I've ever seen, and I've worked for NASA for 25 years, if their contractor says no, in the end, they'll stand down. They will not go against the contractor. But all they end up doing is pressuring the contractor to say yes, and that makes them feel better, right? It's weird, but that's the way NASA
They're
works.
not responsible at that point.
Yeah, it's CYA, is really what it is. So the telecon resumed at 11 p.m. A Thiokol vice president said the data was inconclusive and the company recommended launch, right? This was not the VP of engineering. This was the other VP in the room. That's something that's important to remember, right? In the end, he couldn't, as the engineer, say yes, but he also couldn't say no because he realized what was at stake, right? So that's the biggest issue behind this. And this will happen to you, not right now, not when you're an undergrad or even when you get out, but eventually you'll become a big manager of a company. And these kinds of things happen, right? And so that's what this is about. It's more to make you reflective of, well, what would I have done, And so that's the big thing. So Marshall, being the way it was, and still is, asked for dissent, and none was given, right? Al McDonald refused to sign the launch authorization on behalf of Thiokol because he was the engineer due to his own concerns about the cold temperatures. So a Thiokol official in Utah had to sign off on the launch and fax that authorization to Florida, right? That is the one thing you need to remember, is that NASA required that authorization signed to them. That was their CYA, right? That was a big deal for them, and that's still that way. In that room, I knew several of the people because I worked with them at Marshall, and it's amazing to think about them after that, after them being in that room. But that's what happened, right? The one thing you need to know is the astronauts were never told this happened. No one was really ever told outside of that group that any of this happened. All that anybody in Florida saw was that signed document saying go for launch, right? So that's a big deal, All the communication didn't happen. Now, back in 1986, communication wasn't like what it is today. We can send and text each other and be done, show the launch or not.
Someone would have tweeted it.
I know. But back then, this was a huge deal. But that's a big thing, is communication, right? To get all that out there. So, we come to launch day, right? That's what it looked like. So you can see all the ice hanging off everything, because they had sprayed the pad down, because they had liquid oxygen, liquid hydrogen out there. Ice was everywhere. The biggest concern of the launch team was that there was ice on the pad and there was ice on the arm of where the astronauts walked. And in an emergency, they have to run down there and get in a basket and fly down to the bunker, and they were afraid they might slip and hurt themselves, right? That was the biggest concern of that morning, not that the solid rocket booster could fail. So that's a big deal to me too, because I'm always like, God, that was the least of their worries. Mm-hmm. That was the thing they were most concerned about. If you ever watch the video of that day, there's a lot of people out here in hard hats looking up at this ice, because they also were worried that the ice might fall off and hit the orbiter and bang its tiles or rip through the external tank, which we found out on Columbia. That was a bad thing too, right? But that's the way this worked. So then this is what happens. So at launch, because it was so cold on this solid rocket booster, the right solid rocket booster, instantaneously at launch, because it was so cold that day, the primary and the secondary O-ring shattered into a million pieces. the second it launches. And the reason we know that is because of that puff of black smoke right there, right? Smoke is already coming out. That's actually the soot coming out. The putty's out, right? So now there's a perfect path. And something else you need to realize is, right, each of these joints has O-rings, right? If it would have been one of these joints, it would have probably been okay. But it was the one right here next to the connection point to the solid rocket booster to the external tank. And that was the worst one it could have been, and that's exactly the one it was, right? Now the problem also is, no one saw this in real time. This is post-fact. When they started looking at it to figure out what was wrong, they saw this puff of smoke right then, right? But something you need to realize, because everyone's always had this theory of, well, they could have aborted the mission. Oh no, they had lit the solid rocket boosters. That means you're going to go somewhere. The solid rocket boosters with the main engines means this thing is going to move and go somewhere. And for the first 2.5 minutes, all the way through the solid rocket burn, you don't have anything to do but go up. You know, you can't abort, you can't get out of the way. There's nothing that can happen with this thing. Even after Challenger, when they put in the escape hatch, didn't matter. You couldn't do anything in the first 2 minutes because you're shooting up through the atmosphere so fast to get away from gravity, really, right? So that starts happening. So then what happens after the soot gets out of the way, there's now a nice little path for the flame to go out, right? And so that's what starts happening. So you can see when they went back and looked at the footage, there's the flame, bigger flame, bigger flame, bigger flame, bigger flame, bigger flame, right? So what that flame is doing is it's sitting there looking at the strut that holds the solid rocket booster to the external tank. This external tank is basically like a hydrogen bomb. Inside here is liquid hydrogen and liquid oxygen is in the top, okay? So that's what's burning for the Space Shuttle main engines down here, right? That's what they're using. But it's basically a gigantic bomb just waiting to go off, right? So this flame keeps licking at this steel, solid, really tough, thing. So it takes a while for it to do it. It licks through it, burns through it, basically, right? And coincidentally, at the time that this fine thing finally breaks through, it's called maximum dynamic pressure, max Q, which is when the shuttle has to throttle down so it doesn't go so fast it doesn't rip itself apart. So you're basically shaking the most violent you can be at the same time this thing just broke free, right? See, everything happened exactly at the right time to make this work, right? So then you have a solid rocket booster that's free on one end. So it starts tilting. It starts doing this, right? Coincidentally, on the stage Challenger lifted off, the upper level winds were the highest they've ever been. So the shuttle was pushing itself to get it on its way up because the wind was trying to push it one way and the orbiter and the engines would push it back on course, right? Because that's the job of it, is go to that point in space. So all that was happening at the same time. So you've got this vibration, this whole thing, it rips apart, it turns out, and the shuttle goes, wait, we're going the wrong direction. So it turns itself back into it and it makes the solid rocket booster hit the external tank and it explodes the entire back end, which is liquid hydrogen. So it just goes down here and ignites because there's flames all down through here, and then it starts shoving everything up, and that's when the big explosion happens. From our perspective and watching the video, this happens almost instantaneously, but it just goes and then it's gone, right? So 73 seconds after launch, she's gone, right? The famous thing is Michael Scobie, I think is the one who does it. Dick Scobie and Michael, what's his name, the pilot? Can't remember his name. They go, Challenger, go for throttle up. And he goes, Roger, go at throttle up. And he goes, because it's over, right? Because they just went through max Q and it had just been through all that. And then they fire the engines up. They push the engines full throttle and they go on up into space. And what should have happened, right? So this is a timeline, right? Puffs were leaking from the O-ring within 1 second of the flight, right? At 59 seconds, the flame is visible from the O-ring. At 64 seconds, the external tank is breached. At 72 seconds, the booster begins to rotate and the fuel tank collapses due to structural failure, right? The thing about this is when all that happens, the shuttle actually goes a lot faster than it's ever went before in its life during that part of the mission. It's because all that propellant got ignited, so it just pushes it up, right? So the fuel tank, it's the hydrogen tank, an inner tank, and then the oxygen tank. It just shoved it up, basically, and shoved up the hydrogen tank into the oxygen tank, which then made the whole explosion, because then it had an oxidizer to really go after it, right? Then at 73 seconds, explosion and destruction of the whole entire thing. It was traveling at Mach 1.92 at about 46,000 feet altitude at that time, right? The problem is the solid rocket boosters, if you ever noticed, they veer off. They broke off from it, and they're going. One of them was actually going towards Daytona Beach, Florida, because they weren't that high up. And so the range safety officer had to actually auto-destruct them about 110 seconds after the launch, right? Or 36 seconds after the explosion to get rid of them so they didn't hurt more people. Everyone always thought that was a big cover-up, that they were trying to get rid of the evidence. But no, in reality, it was the fact that they couldn't let other people get hurt by this, right? So the biggest thing also you need to realize is the shuttle, the way it is designed, right? This is the crew compartment right here. That thing is ungodly designed. I mean, if you ever get to go in them, because now they're on display in museums, they're unbelievably designed. It's a very strong pressurized compartment. Everyone had hoped that in the explosion they all died. They actually found out in looking at video, this thing gets ejected out from the overall explosion, the fireball, right? And so they got ejected. So everyone thought, well, okay, maybe they had a lot of G's that knocked them unconscious, no big deal. They actually now know, they've released the footage and the documentation now. Several of them survived all the way down, probably till the splash, because the splash killed them. It was such a violent thing into the ocean. But they know for a fact that the pilot and commander, their emergency oxygen is actually behind them. So the two astronauts sitting behind them would have to hand it to them. Those tanks actually had been depleted. So they were alive on the way down, which was kind of the scariest part. Because everyone had thought, oh God, at least they died instantaneously. They never knew what was happening. No, they knew it all the way down. Is what it looks like now. So that's Challenger, right? So the really cool thing for me, I watched this in 5th grade. This actually made me want to go in the space program, which made me then come to space camp, where I found out there was this place called UAH, and everything kind of changed for me in my life, right? And January 28th is like a really big day for me. I actually became Dr. Benfield on January 28th, 2005. So for me, Challenger is a huge deal. It kind of made me what I am today, which is kind of weird, but that's why.